Hello, everybody. Thank you so much for joining us for today. We have another great webinar here from Quantum Analytics. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. Today, we're going to be exploring the topic of rapid catalyst screening. Understanding the performance of catalysts is a big deal in manufacturing environments, but the evaluation process can be extremely slow. With typical evaluations taking anywhere from a week to several weeks, scientists and process engineers have been asking for solutions that rapidly characterize new catalysts without sacrificing accuracy. So to address this topic, I am super excited to welcome my colleague and friend, Rogine Belganet, with us. Rogine is the technical director at Frontier Lab Americas. Rogine is very passionate about creating awareness around the frontier technology and providing technical support to customers. Rogine graduated from the University of Houston with a Bachelor of Science in Chemistry, and she started her profession as an analytical chemist at Nalco Champion, an Ecolab company, in 2012. And as an analytical chemist, Rogine has worked with a variety of analytical instruments, such as pyrolysis, GCMS, TGA, FTIR, and X-ray for material characterization, polymer identification, and contamination analysis. Before I turn it over to Rogine, I wanted to give a little bit of an intro to quantum analytics. Quantum Analytics is a value-added distributor of multi-vendor instrumentation. We've been a channel partner for Agilent Technology for actually over 30 years at this point. We specialize in cross-platform integration, training, and application support. What we're really known for from our clients is our flexible financing, rentals, and leasing programs. And we are also a really great resource for new and refurbished instrumentation. So let's go over a little housekeeping items before we get started. Everyone who registered today is going to get a link to this recorded webinar in your email when it becomes available. This is usually about a day later, so in about 24 hours. We think this webinar is going to be about 30 minutes. Then we'll open it up for questions. Type your questions at any time in the question box that you see in the webinar panel over to the side there. Rogine will be answering questions at the end of the webinar. So that ends our intro. So without further delay, let's get started. Rogine, it's over to you.
Thank you very much, Lauren, for the introduction. All right. So I'd also like to start with a brief history of Frontier Lab. We are a global corporation with three main product lines. We have our microfurnace pyrolyzers and their accessories, µ-Reactors for rapid catalyst screening, and also a line of ultra-alloy stainless steel capillary columns. And in today's presentation, we will actually focus on the µ-Reactor product line. And you will hear about some of our accessories, such as the microjet cryo trap or the selective sampler, but we will not go into detail of the accessories, but we have many available resources, such as the on-demand videos and presentation that discuss these accessories. Or you could always connect with us and we can discuss about the accessories and their application in more detail. So here is the agenda for today. We will first discuss why we developed µ-Reactor product line in addition to our microfurnace pyrolyzers. And then we go over the system configuration of the µ-Reactors, both the tandem µ-Reactor and the single µ-Reactor, and also we learn how they function. And then at the end, to demonstrate the capability of this product line, we will show a couple of short application notes. Before we start talking about the actual µ-Reactor product line, I wanted to quickly talk about the differences between a µ-Reactor and a pyrolyzer. And by the way, both of our product lines, both the pyrolyzers and µ-Reactors, are based on the microfurnace technology that are used in conjunction with a GCMS system. So the microfurnace pyrolyzer mainly is used for polymer characterization by pyrolytic analysis. You could use qualitative and quantitative analysis for polymers and additives with mid to high molecular weight, typically 100 to more than 10,000. Microfurnace pyrolyzer also allows GC analysis of gas, liquid, and even solid samples without any pretreatment. On the other hand, the µ-Reactors aim to shorten the development period of a new catalyst by quickly and effectively evaluating the function and the performance of the catalyst. It can evaluate the type and amount of compound produced by the catalytic reaction, as well as the optimum temperature and the pressure. The molecular weight of target compounds is typically low, around 100 or less. And with the Tandem µ-Reactor, the pyrolysate by pyrolysis and the catalytic reaction products with the pyrolysate can be evaluated at once. A GCMS system, which is often very difficult to use with conventional catalyst evaluation system, can be used in this case with µ-Reactor, and various temperature control modes of µ-Reactor enable several catalyst evaluation from a new perspective. So this is the question that we often get, why we did develop µ-Reactor technology. Since catalysts are a very important material in our lives and many industries, scientists like you are always looking for new and more effective catalysts. And they want to quickly evaluate how the catalysts work and what the optimal reaction conditions are. However, as you know, the conventional catalyst evaluation systems have large reactors and in most cases require a huge amount of time, typically several hours, for the temperature to stabilize. So it can typically take 1 to several weeks to evaluate the entire catalyst. Rapid development of new catalysts now requires a significant reduction in the evaluation time. So we developed a µ-Reactor as a laboratory scale, like a benchtop evaluation system to meet this demand. The µ-Reactor can make the period of catalyst evaluation shorten to only several hours or several days. And the online connection to a mass spectrometer instrument, which is very difficult, as I mentioned, on conventional catalyst evaluation system, is available, while more effective, more efficient, and also more rapid catalyst evaluation is achieved. So what factors did we consider when developing this technology? We really focused on 3 main factors to solve the problem of conventional catalyst evaluation systems. 1, the technology must have a simple design. We know very well in catalyst analysis that many catalysts must be evaluated. So the exchange of the catalyst needs to be done frequently, easily, and rapidly. Now, our µ-Reactor technology is a laboratory scale small instrument with very easy exchange of catalysts and a simple maintenance. 2, the temperature is also an important factor in catalytic reaction. Precise temperature control must be required for exact evaluation, and the ability really to rapidly heat and cool the reactor is very important for many catalyst evaluation in short term. And our µ-Reactor provides and guarantees there's this precise temperature control. And then lastly, the third factor was the rapid analysis of catalytic reaction products that can be achieved. And our µ-Reactors can be used for online GCMS analysis, is the gas chromatography mass spectrometry analysis, by directly installing on the GC injector, so there won't be any transfer line. They have various temperature control modes, such as isothermal, linear, and stepwise, and I will discuss all those temperature modes in more detail shortly. For example, the temperature of the catalytic reactor is automatically changed, and the reaction products at each temperature can be analyzed automatically as well. I think now we have a good background about why did we develop this technology, what factors did we use while developing this technology, and now let's go ahead and jump into the actual technology for the µ-Reactor. So our µ-Reactor product line, as you can see here, for rapid catalyst analysis consists of 2 main products. We have the Tandem µ-Reactor, and also we have a single µ-Reactor. And this is the general system configuration of the µ-Reactor GCMS system. Here I'm showing the Tandem µ-Reactor, but that's exactly the same for the single µ-Reactor as well. So the microreactor, either the tandem or single, as you can see here, is actually directly connected to your GC injection port. No transfer line and no cold spot. The microfurnace technology also allows a continuous analysis where all the pyrolyzates are directly and continuously are deposited in the GC system once the catalyst reaction happens. The reactor flow controller, the ultra-alloy capillary column, EGA tube that I will talk shortly about, and also the vent-free GCMS adapter are standard items contained in both of tandem and single reactor packages. But there are also other accessories or additional items, such as the auto shot sampler that can automate the process of your analysis, selective sampler, and also microjet cryotrap that are optional items. And I want to note that the auto shot sampler is only available for the tandem microreactor. It's not compatible with a single microreactor. And as we go through this slide, I'll explain as much as possible about these additional accessories. But as I mentioned at the beginning, if you would like, we could provide more information about these accessories as well. But today we'll mainly focus on the microreactor technology. First, we're going to start with the single microreactor. And here you can see the system diagram of a single microreactor. So single microreactor, as the name can kind of mention that to you, only consists of one reactor or one microfurnace and one flow controller. So 3 different gases can be connected to the reactor flow controller. And since there is only one reactor that contains the catalyst bed tube, only gas and liquid samples can be analyzed. No solid sample if you try to use the single microreactor. Now, introduced sample makes catalytic reaction in reactor, and the products flow into GC injector directly and then are analyzed with GCMS or a direct MS. Reaction gas can be selected with 3-way valve and introduced to the microreactor. For example, hydrogen can be used for your reduction reactions, or you can also use oxygen and air for oxidative reaction. These gases are switchable using the reactor flow controller easily and by connecting each gas tube to the controller in advance. Each gas flow rate is also individually regulated by the individual mass flow controller, as you can see here in this picture. Now, if the reaction gas, such as oxygen, which cannot be used as a carrier gas in your MS system, is selected, then the selective sampler and microjet cryotrap accessories must be used. So in this case, if, say, for example, you choose oxygen as your reaction gas, oxygen gas needs to be diluted by a carrier gas or needs to be replaced with a carrier gas after reaction happens, which is before separation analysis on GC. Because as we know, oxygen can damage your column phase and also your MS. So when you replace the reaction gas with a carrier gas, you would also need to use the cryotrap to trap the products on the head of your GC column, and you would also need to use the selective sampler for the switch of the gases. So a quick note about microjet cryotrap, that's an accessory that uses a liquid nitrogen, and it will trap and focus all those volatiles and light compounds at the head of your GC column. And the selective sampler is an accessory that selectively allows you to pick and choose which zone of operation you would like to send it to the GC column for the separation and analysis and getting the GCMS chromatogram, and which portion of your sample you would like to vent out and not obtain the GCMS chromatogram for. Now here is the diagram of the tandem microreactor. So the tandem microreactor consists of 2 reactors or 2 microfurnaces connected in series and with one flow controller. First reactor is used to preheat a gaseous sample or vaporize a liquid sample or even pyrolyze a solid sample. So in this case, you can actually use solid, liquid, and gas samples using the tandem microreactor. And then your second reactor will be used for the catalytic reaction with the catalyst tube. It has a quick change catalyst reaction tube, and the temperature of the reactor can be programmed through a variety of heating modes, as I mentioned, such as isothermal, linear, and a stepwise program. And just like the single microreactor that we just talked, 3 different gases can be connected to the reactor controller, and the flow rate of each gas can be controlled easily by a separate mass flow controller. And as we mentioned again, if you select a reaction gas such as oxygen, which you really cannot use it as a carrier gas, then the selective sampler and the microjet tri-trap accessories must be used. So I thought to share with you guys some of the specification, and this is just one page of the specification. Of course, we could provide more, but you could see some of the parameters and the specification of both tandem microreactor and single microreactor in this slide. In tandem microreactor, the maximum temperature of the first reactor is actually 700 degrees Celsius if you use a stainless steel tube, but it can go up to 900 degrees Celsius if you use a quartz tube. And that's where the pyrolysis happens in the first reactor for your samples. And then the maximum operating temperature of the second reactor of the tandem microreactor, or the reactor of the single microreactor, is 800 degrees Celsius. So both reactors can be interfaced with a GCMS, a spitless injector, and a compressed gas such as air or nitrogen is required for cooling the reactors. And as I also mentioned, when you purchase either of the microreactors, you will also get the vent-free GCMS adapter that allows you to quickly switch columns without venting your MS. You also will receive the ultra-alloy capillary column that is a 30-meter long column with an inner diameter of 0.25 mm, and also a catalyst tube that is packed with Zolite ZS5M catalyst. So for the preparation of the catalyst and really installation it to the microreactor, you easily pack the catalyst in the catalyst tube, and then you insert it into the microreactor, and that's pretty much it. The catalyst tube is made of the quartz glass, and that is because the quartz glass has high inertness, as we know, and it has high durability against high temperature, and the state of the catalyst can be visually observed. Also, sometimes the deuterated catalyst changes the color, as you know, and that can be checked easily because of the transparent nature of the quartz tube. And the catalyst is packed in a catalyst tube, as I mentioned, and shown on the right figure. A small amount of quartz wool are also placed both at the bottom and the top of the catalyst bed to keep it in position. And the figure on the right shows the packed catalyst reaction tube inserted into a deactivated steel tube. And this is for your second reactor of the tandem microreactor. In the case of single microreactor, the catalyst tube can be easily removed by only opening the liquid sampler. And the liquid sampler is pretty much just a sampler that closes on top of the reactor. So you just easily open that, and you could, using a tweezer, pull out the catalyst tube. And in the case of tandem microreactor, because your catalyst tube is in the second reactor, you will remove the first reactor, and that's pretty easy. The first reactor and the second reactor are connected via a needle. So you just disassemble the first reactor and you just pull out the catalyst tube from the second reactor. So the thermal profile of the catalyst reaction tube inside the second reactor between 100 to 700 degrees Celsius is shown in this figure. And from this temperature profile, it can be seen that at each set temperature, which is 100, 300, 500, 700, the catalyst bed is heated uniformly within a range of 40 mm. In fact, the temperature variation within a 40 mm length of the catalyst bed is only plus or minus 0.1 degrees Celsius. So in order to uniformly heat the entire catalyst, the height of bottom quartz wool must be 10 mm or higher, and the total height of bottom quartz wool and catalyst bed must be less than 50 mm. The upper quartz wool is just to prevent the catalyst scattering by sudden pressure changes, and typically the height of the top quartz wool we suggested to be somewhere between 10 to 20 mm. So this diagram really shows the catalyst evaluation process using the µ-Reactor system. So first, as we discussed, catalyst is packed in the catalyst tube and the reaction tube is fed into the reactor. So in case of a solid sample that we are using a Tandem µ-Reactor, the sample can be placed easily in an inert sample cup and introduced into the first reactor of your Tandem µ-Reactor. In case of liquid or gas sample, microsyringe is also available for sample introduction, and you could either use your Tandem µ-Reactor or a single µ-Reactor. Gas, liquid, and solid samples then can be analyzed, but solid samples, as I mentioned, can only be analyzed using Tandem µ-Reactors. Then the introduced samples are heated in a µ-Reactor. Liquid and solid samples are pyrolyzed in the first reactor of Tandem µ-Reactor, and the pyrolyzates flow into the second reactor, which is the catalyst reactor. The gasified samples are introduced into the catalyst and converted to products by catalytic reaction. The products by catalytic reaction are then introduced into your EGA tube or the separation column through the GC injection port, and which is a direct connection, by the way, and the products are monitored by a GCMS system. So a quick note, because I've been using EGA tube term, a quick note about EGA tube. EGA stands for Evolved Gas Analysis. That's one of the mode of operation of the pyrolyzer, and that's a thermal analysis of your sample. EGA tube, which actually will be provided to you when you purchase either of the µ-Reactors, is just a short and deactivated tube that connects the GC injector to the MS and is not a separation column. So you could use a real-time monitoring using the EGA tube, or you could do any type of the separation analysis using your GC separation column. So there are two main products. There are two main ways in introducing your sample into your µ-Reactors. One is the flash injection that can be done either using a microsyringe for gas and liquid samples in Tandem µ-Reactor, or if you have a solid sample, you could just easily place it into an inner sample cup. And then second is the continuous feeding. And in this case of continuous feeding, if you have a liquid sample, a solvent vapor with carrier gas by bubbling can introduce the sample into the µ-Reactor, or a syringe pump, as you can see here, can also be used. For gas sample, gas flow rate is regulated by reactor flow controller and is introduced to the µ-Reactor. So with the continuous feeding way of introducing your sample into the µ-Reactor, sample introduction to separation column with a certain period of time, or the sampling time, can also be done using your selective sampler. And when the target is a volatile compound, the compound can be trapped properly by cooling down near the separation column inlet by microjet cryotrap wall sampling. So for gas piping, using both Tandem µ-Reactor and single µ-Reactor, here we are showing some examples. For the Tandem µ-Reactor, example 1.1 shows that a carrier gas is supplied to the top of the first reactor, and then a reaction gas is supplied to between first reactor and the second reactor. Example 1.2 shows that a reaction gas is supplied to the top of the first reactor, and a carrier gas is supplied to GC injector and dilutes reaction products and a reaction gas, and then flow into GC separation column or EGA tube. And example 1.3, all the way on the right-hand side, shows that a reaction gas is supplied this time to the top of the first reactor for pyrolysis, and another reaction gas is supplied to between first reactor and the second reactor for catalytic reaction, and then a carrier gas is supplied to the GC injector. That's the same concept that we just discussed a few minutes ago. If you pick something like oxygen as your reaction gas, which you could not use it for your carrier gas, you either have to dilute it or replace it with the carrier gas whenever you want to send it to your GC column. And the main purpose for it is to protect your gas. Now for the single µ-Reactor at the bottom, example 2.1, shows to make catalytic reaction with only a carrier gas and make the products flow into GC column. Example 2.2 shows the gases which are mixed in advance, and then the mixed gases supplied to the top of the microreactor. And example 2.3 shows to make catalytic reaction with the reaction gas, and a carrier gas is supplied to the GC injector. And these are only some examples that we are showing here. You can also customize the gas piping based on your own application. Now let's talk about the temperature programming modes for these microreactors. So both tandem and single microreactors can be used in 3 different temperature modes. They could be either isothermal, linear temperature, and stepwise temperature. And you could see screenshots of the control software on the right-hand side, where you can actually choose the first reactor versus the second reactor tab, as shows on the control software. Also, you could, by clicking on either of those modes of programming, either could be linear, stepwise, or isothermal as well. But in the case of the linear temperature analysis mode, that mode is useful to investigate the suitable reaction temperature range. And I'll show some example on this one via our application notes. And in this case, with the linear analysis, the EGA tube must be used and is connected between the GC injector port and the MS in your case. So there is no separation column. And the sample introduction must be based on the continuous feeding. The reaction products that are generated depending on the temperature rise of the reactor are directly observed by the MS in this case. So it's a real-time monitoring that allows you to obtain the optimal temperature for your catalyst analysis. Now with isothermal temperature analysis, this one is very similar to your flash pyrolysis, using the separation column. So in this case, you would use the separation column. And the furnace is kept at a constant temperature, and the sample is introduced with flash injection or a continuous feeding. That's up to you. And you can also use a selective sampler to introduce the catalytic reaction products into the separation column for a certain period of time. Now, the last one is the stepwise temperature mode, which is an effective way to automatically collect chromatograms at multiple set temperature. So when the target is volatile compounds, then the microjet cryo trap is also needs to be used, as we mentioned. And for the stepwise temperature mode, the sample introduction must be continuous feeding. Sampling of reaction products is regulated by selective sampler. The reaction products are introduced into your GC separation column during a certain period at setting temperature. So GC separation analysis starts after the selective samplers complete the sampling. Then during the GC running, microreactors stand by at the initial temperature of the next setting temperature. So when GC finishes its run, and it becomes ready for the next analysis, then the selective sampler starts sampling at the next setting temperature and then make the next GC run. So as I mentioned, multiple data and chromatograms can be obtained at different temperature reactions temperature with automatically regulating reactor temperature, selective sampler, and microjet cryo trap when you're using the stepwise mode of operation. Okay, and now the last part, it will be going over a couple of application notes. And the first one, I decided to present the Fischer-Tropsch synthesis over an RU catalyst. So we are using an RU catalyst in this case. And this is one of the major catalytic reactions. So I feel like a lot of us can relate to this. So it will be a good example to show how we would use that for using the microreactors. So FD synthesis converts the cyan gas, a mixture of H2 and CO, to hydrocarbons, as we know. And in this case, we use the sample that is a mixture of H2 and CO gases. Since the sample is in a gas form, we can use the single microreactor, and the sampling was done by continuous feeding. So this first application note I'm showing the single microreactor, and then the second one will cover the tandem microreactor. So for this one, as a sample, we use the gas form sample, mixture of H2 and CO, and on a single microreactor, and we introduce the sample on a continuous feeding. So first, the real-time monitoring with EGA tube was performed on the FT synthesis. And here you can see the EIC chromatogram. So it stands for extracted ion chromatogram. For example, M/Z 15, 18, 28, 44, 41, and 43. And these were the 6 target ions. The sample gas was continuously supplied to the single microreactor, and the flow rate of hydrogen, we set it at 6 ml per minute, and then the CO was 3 ml per minute. So the total flow rate was 9 ml per minute. The reactor temperature raised up to 400 C from 100 C with a 20 degree per minute. So we programmed the micro furnace from 100 to 420 degree per minute as a ramp. And as the temperature increased, the carbon monoxide ion, M/Z 28, of the sample gas decreased. Olefin and paraffin ions were observed in a certain temperature range, which you could see here from 200 to 300 C. And then above 320 C, the ions of olefin and paraffin disappeared, and the ions of methane and water increased instead. Since the target compounds were olefin and paraffin in our case, the optimal temperature range was identified to be 200 to 300 C. So that's the first step that I mentioned, that it's a real-time monitoring you would use to identify those optimal temperature for your catalyst analysis. From the real-time monitoring, as we just saw, we were able to identify the optimal temperature range for getting those olefins and paraffins. Next, the separation analysis is the next step to perform on a sample. So the EGA tube was switched to the separation column using the GCMS vent-free adapter without shutting down the MS. And we also used the microjet cryo trap and the selective sampler accessories and set the temperature as we got it from 200 to 300 C. And these are the chromatograms with reaction product that were obtained at each reaction temperature from the isothermal temperature mode of the single microreactor. So you see we actually started from 180 all the way to 320 C. The individual compounds can be observed as peak, and also it can be used for quantification analysis. So in summary, the temperature range at which the paraffins and olefins are produced were easily identified by real-time monitoring using a microreactor coupled online with a GCMS system. And from the separation analysis, we could also conclude that the highest yield of the paraffins and olefins of C3, C4, and C5 are obtained in a temperature range of 240 to 260 C, as you could see here. And this is our second application note. That's the last application note for today. It's the catalytic fast pyrolysis of the rice straw over Zolite ZSM5 catalyst. So this one is using a tandem microreactor. So in this application note, the gases generated by the pyrolysis of the rice straw were converted into aromatic compounds, benzene, toluene, xylene, naphthalene. And since the sample was solid, we are using the tandem microreactor, and we use the flash injection to introduce the sample into the microreactor. We also use microjet cryo trap and also the separation column along with the tandem microreactor GCMS system, as you could see on the left-hand side. First, a rice straw sample was placed into an inert sample cup and pyrolyzed in a first reactor at 500 degrees Celsius. And then the pyrolysate flow into the catalyst tube in the second reactor and made a catalytic reaction at 500 C with ZSM5 catalyst. And these are the temperature that we set, and you could set customizable to your needs. Right top chromatogram is actually the pyrogram of the rice straw without catalytic reaction. And as you could see, many pyrolysate of rice straws are observed. And that's if you would just do a simple flash pyrolysis using a pyrolyzer on your sample. And then at the right bottom is the chromatogram of the catalytic reaction, products with DSM-5 catalyst. The pyrolysate of the rice straw are converted to some aromatics by the catalytic reaction. Well, I guess I would say for more information on other applications and publication, please feel free to communicate with us or check out our technical note webpage. And with that, I hope by attending today's event, you were able to get some familiarity with our µ-Reactor product line and how you could use this technology for your application. And with that, Lauren, I am done for today's presentation.
Awesome. Thank you so much, Regine. Lots of good stuff covered here. What a really good intro to the tandem microreactor and the single microreactor. This is awesome. So it's time for some Q&A, but before we get into that, I wanted just to let everyone know that we have a ton of on-demand webinars. If this is your first one, joining us today, check out lqa.com/webinars and check out our whole library of on-demand recordings that you can watch basically right away. Lots of good webinars on pyrolysis, FTIR, no matter what you're interested in, we probably have something there for you. So definitely check that out. All right, let's dive into the Q&A. First up here, what do you do for components on the MS that overlap in mass, such as nitrogen, ethane, ethylene, carbon monoxide? Oh, sorry, Rosie, I don't know if you're...
Yeah, I was on mute.
That's okay.
So if I am understanding the question, if you are co-loading pretty much peaks on your MS, you could either use the EIC's extracted ion chromatogram to see if you're able to extract that using a unique quantification ion or the EIC's extracted ion chromatogram. Or sometimes maybe even the temperature that you're setting your analysis, depending on what you're trying to do, that's the right temperature to be able to thermally extract them at different temperature zone and be able to get the different or separate peaks. But one common thing that we used to do for our phthalate ASTM method, when the phthalates were co-loading together, the way to distinguish them was using a unique quantification ion to be able to distinguish them.
Fantastic. Next question here is, how is quantitation accomplished? There's no fixed volume sample loop for gas injection. Are the results just relative abundance? Can you calculate mole or weight percentage of the reaction products?
That's a good question. So typically they are done as a semi-quantification work, and you do have the intensity of your detector, in this case as the MS. Now you could record the weight based on the volume and do the calculation of your sample that you're trying to do based on the catalyst and based on the actual amount of sample that you will put into your first reactor and calculate that. But typically there are weight percentage and it's a semi-quantification work on those samples.
Fantastic. And then how long does it take to change out a catalyst sample, including cool down and heat up times?
So depending on what's the temperature that you set your microreactor to go up to. So is it 700, is it 500, 800, coming back to the room temperature. But because it is a microfurnace technology is based on a low mass ceramic heater that cools and fast pretty quickly. So in a minute of, in a range of a few minutes, could be 2 minutes to 4 minutes, depending again of how high of a temperature you have, you could bring it down, cool it down. And the heating is also pretty quick because again, the technology is based on a low mass ceramic furnace that you are using.
So my next question, I think you kind of tapped into it, but probably just good to address this directly. Is there a way to heat the catalyst greater than 700 degrees Celsius? And what is the limiting temperature? And can it be, what is limiting the temperature and can it be changed?
So the maximum temperature for the first reactor, if we're talking about the tandem, since you have two reactors, you could do actually 900 C if you use a quartz tube, 700 C if you use a stainless steel deactivated tube. And the second reactor, it goes only to 800 C. So that will be the maximum temperature that you could do for your catalyst analysis. But the first reactor will give you a little bit higher, go up to 900 C in case you need to pyrolyze in a higher temperature.
Awesome. And remind us, what gases are required to use the tandem microreactor?
So typically you use helium as a standard carrier gas, and that's pretty much given with the GCMS system. But for the reactors, you would need compressed air or nitrogen that is used for cooling your furnace.
And then how can I pack the catalyst into the reaction tube?
So this can be done very quickly, very easily. You have your reaction tube and you just basically put and place in your catalyst inside of it. And the bottom and the top of it, we suggest to put some quartz wool, as I just showed some calculations about 40 mm. That's the uniform amount of heating of the catalyst, but very easy, very quickly. You could also switch it, or you could use a different tube, but in that case, just place some inside your tube, the bottom and the top, use the quartz wool, and that's it.
Fantastic. And then what is the size of the catalyst reaction tube?
So the size of your catalytic reaction tube, it is about 4 mm outer diameter and about 3 mm inner diameter, and is made of a glass, a quartz glass tube.
Ooh, this is a good one. I think we've had a lot of questions relating to this. So if you have a multi-shot pyrolyzer, can you just add the second reactor of the tandem to your current configuration and turn it into a tandem microreactor?
So because the temperature control and the sizes of the microfurnace pyrolyzer is different than our tandem microreactors, the answer is no, you cannot do that. But we have many customers who, if you already have the multifunctional pyrolyzer, you could kind of use it as a single microreactor in a way that you place your catalyst inside your cup with your sample and just inject it into your pyrolyzer system. It's not the same as the single microreactor, but if there are applications for you to be able to mix the catalyst into your sample, place it into that cup, and the cup is only 80 microliters, so there will be some limitation of doing this, but it's possible. But the short answer is because the size of the dimension of the controller are different and the size of the instrumentations are different. So no, you cannot just connect the second reactor to the pyrolyzer.
Fantastic. Well, I think that brings us to the end here. Before I close, I just want to thank everyone for attending the session today, and thank you, Rogine, for sharing your knowledge and expertise with us. We encourage everyone to visit the resources page on lqa.com for future webinar details and to check out that list of recorded on-demand sessions. So thank you everyone again, and have a great rest of your day.